Assalamu alaikum and welcome to lecture number 3. In this lecture we are going to discuss about the LTI systems in frequency domain, the Fourier transform, discrete time Fourier transform and its properties, and interconnection of LTI systems. LTI systems in frequency domain. Recall that we have studied discrete time signals in time domain. We express the discrete time signals in terms of scaled and shifted impulses, which is of the form this one, right, where k is integer. This led to characterization of LTI system in terms of impulse responses. And once we can represent the signal in terms of scaled and shifted impulses, and we know that the system is LTI, so by just knowing the impulse response of the system, we can find the output of the system using the convolution. So you understand, in general, convolution is very tedious and to compute, right? So you flip, you shift, and you multiply. So that's a very tedious work. So here we are going to study another representation of the signals and LTI system. We aim to develop a frequency domain analysis of signals and LTI system, and this representation is an extremely important. Here we'll study discrete time signals as linear combination of discrete time complex exponentials of the form this one, right? So if you compare with the previous one, here we were expressing the signal in terms of scaled and shifted impulses, and by just knowing the impulse response and knowing that the system is linear and time invariant, we can find the output using convolution sum. So here, if we can represent a signal in terms of discrete time complex exponential signals of the form this one, e power j omega k, where k is integer. This will lead to the Fourier transform representation of discrete time signals and characterization of LTI systems in terms of their frequency responses. So, for example, we have a discrete time system H. So there may be certain inputs x of n such that the output is a complex number times the input, that is output equals to lambda times the x of n, where lambda is a complex number. In such cases we call the input as eigenfunction, right? So the input is eigenfunction of the LTI system, and the complex number is the eigenvalue of the system. So this is x of n is the eigenfunction, okay, and lambda is the eigenvalue for the LTI system. For an LTI system with given input xn and impulse response hn, so we can find the output using the convolution, and which is h of k x of n minus k. Now we assume that the input is e power j omega n. For fixed value of omega, we can write the output as y of n equals to summation k running from minus infinity up to infinity h of k, and the input is e power j omega n, so x of n minus k will be e power j omega n minus k. Now if I open this, because we are summing it over the k, so that means this term will consist of e power j omega n times e power j e power minus j omega k. So e power j omega n, because we are summing it over k, so we can take that common, right? So we can take it out here and we say that this one. So now this is your input e power j omega n, and this times this one, right? So let we represent this whole by lambda, so we can say output equals to lambda times the input x of n. So that means the discrete time complex exponential e power j omega is an eigenfunction of the LTI system, and the eigenvalue lambda is a complex number that depends on specific value of the omega and on the impulse response Hn, right? So we can write the frequency response as if you look at from the previous slide, we can say that h of j omega basically equals to summation k running from minus infinity up to infinity h of k e power minus j omega k. So that also means this is the relationship that tells how we can, if we are given the impulse response, how can, using the impulse response, how can we find the frequency response of that LTI system. Note that while x of n and y of n and h of n are discrete time signal, their domain is time, right? And n is member of n is has values of integer values, right? But the frequency response is a continuous signal whose domain is continuous, that is omega, right? So omega is basically real. Since possible discrete time exponentials can be created using frequencies omega in the range of this, you understand, if you recall, you have done this in signal system, that a discrete time signal can have maximum frequency of from minus pi up to pi, or you can also say that it is from 0 up to 2 pi. After 2 pi it repeats. That means the high frequency signals are near to the pi or minus pi, and the low frequency signals, they are near to 0 or 2 pi or integer multiple of 2 pi. We intuitively expect that h e power j omega, which is frequency response, is also periodic with period 2 pi in omega. This is in fact the case because if we have, for example, h of e power j omega plus 2 m pi, so this can be written as this one, and again if we split this one into e power minus j omega k times e power minus j 2 m pi k, so this basically, this is equal to 1. This we have done. So that means this is basically equal to e power minus j omega k, right? So that means e power j omega plus 2 m pi basically is same as h e power j omega. Hence we usually graph h of j omega over one period, either from minus pi to pi or from 0 to 2 pi, because after this they repeat. Thus frequency response of any discrete time system is continuous function of omega, and it is also periodic with period 2 pi, right? So these are two important points, that for the frequency response of any discrete time LTI system is continuous function of omega, and it is also periodic with period 2. Since eigenvalues are generally complex, so h of e j omega, which is right, which is a eigenvalue of LTI system, is also complex, right? So if something is complex, we can represent it in terms of polar form, which rectangular form, which is we write it as a sum of the real part and imaginary part. You understand? J signifies that this is basically imaginary part. Or we can also express the complex numbers in terms of in the form of polar form, right? So in polar form we write it magnitude and the phase, right? So absolute h of ej omega is basically magnitude response, and ej angle h of ej, this is basically the phase response of LTI system H. So for example, we take a numerical example and we say x of n equals to a into e power j omega n. So again, you see that this is a complex exponential signal. So if the signals are complex exponential, then they are eigenfunction of the LTI system, right? So in this case, we can say output is basically equal to frequency response times the input signal. Remember that input signal must be expressed in terms of complex exponential signals, right? So that means if you multiply this one with this, so the input signal is a e power j omega n, so it will be a, right, h e power j omega n times e power j omega n. So we get the same signal, whatever we give it at input, we get the similar how to say, the eigen, right, of the signal. So we give it as input a e power j omega n, and we get the output as a h e j omega n e j omega n. So this is the scaling factor, or right, which is also called as the frequency response of the system. Okay, so we can write in a polar form the output as a times magnitude of the frequency response. Okay, and this is the phase response of the uh, system, and this is the input, right? So you represent basically the frequency response in terms of magnitude and phase. Okay, so this can be simplified to this one. Okay, because this is angle and this is also angle, so they are multiplied, so the angle will be, the resulting angle will be sum of this and this. Okay, so we can say that, so this term can be written as cos of omega n plus angle of this plus angle introduced by the system, and similarly in the uh, plus j into this one. So you understand, you can represent a complex number in terms of rectangular form. So here we are just expressing it. So the magnitude of the output is scaled by a factor of this one. Okay, and the phase is shifted by the this amount. So another example, for example, we have x of n equals to cos omega naught n plus phi. So to find the output, first we represent this signal in terms of complex exponential signal. So you understand, using Euler identity, you can write that cos theta, if I just generally say cos theta, so cos theta equals to e power j theta plus e power minus j theta divided by 2, right? So here we have scaling of a, so that means it will be equal to a over 2 and this one, right? So you know the output is for the case when the input is complex exponential signal, so the output is equal to same complex exponential multiplied by the complex scaling factor, are also called the frequency response, right? So we multiply this one with h of e j omega naught n, and for this part we multiply with e power minus j omega naught n times this one, right? So on simplification you get this. Hope this gives you idea, because such problems we have done in more detail while we were doing the course on signals and systems. So let's jump to the Fourier transform. So you understand, in the continuous time case, Fourier transforms equals to integration from minus infinity up to infinity, the continuous time signals times the e power minus j omega t dt. Okay, and similarly the inverse Fourier transform is 1 over 2 pi integration from minus pi up to pi x of a omega, which is the frequency domain signal, times the e power j omega t d of omega, right? So you understand here we are in time domain, so we will integrate it with respect to time, but here we are in frequency domain, so we'll integrate it with respect to frequency, so that we get the time domain version of this frequency domain signal, right? And again, you understand the Fourier transform is basically in general, a complex function of the frequency variable, right? And it's defined over from minus omega. Omega has range from minus infinity up to infinity, and you also understand because this is complex, so we can represent it in terms of magnitude and phase response, or we can also represent it in terms of real and the imaginary value, which is called the rectangular form. So for the case of discrete time signal, we can represent it like this. So I think you should familiarize yourself with the representation, because in the signal system we had different representation, right? So now we say that for the case of discrete time signal, the Fourier transform is x of e to the power j omega, right? So that's the notation for this one, and this will be again equal to you're, I think, well familiar with these formulas, so you just sum it from minus infinity up to infinity, the time domain signal times the e power j minus j omega n. Similarly, we can find the inverse of this Fourier transform, that is the frequency domain discrete time signal can be converted into time domain discrete time signal using this equation, which is also called the inverse Fourier transform, right? And you understand that omega, right, is real or continuous, right? So that's the notation how we express this. Right, so I hope that's clear to you that if you the frequency domain is the frequency response is basically the obtained by taking the Fourier transform of the impulse response. Okay, similarly we can obtain the impulse response from the frequency response using the inverse Fourier transform, right? And I think in the previous slide we talked about it, that the frequency response uh, is periodic, right, with period 2 pi, and also the Fourier transform of the discrete time signal is periodic with period 2 pi in frequency. Okay, always keep in your mind that Fourier transform of discrete time sequence is 2 pi periodic. Okay, so whether it's a you're talking about the signal or you're talking about the response of LTI system, they both are periodic with period 2 pi. So again, you understand that's the notation, because if something is complex, then you can represent it either in polar form, which is magnitude and phase, or you can also represent it in the rectangular form, where you have the real versus real and imaginary parts, right? So we say this one as the magnitude spectrum, and the this angle as the phase spectrum of x of n. Okay, so it's about when the Fourier transform exists. What about the convergence of inverse Fourier transform to time domain signal? So the condition for a existence of the Fourier transform is that the signal must be absolutely summable. Okay, so that means if you take the summation, so if we take the absolute value, right, because it's absolute summation, so you understand why this is less than or equal to, because here you are summing it, so maybe negative terms, then in that case it will result into smaller values, because those negative will be subtracted. But here you are just taking the absolute value on this whole, so that means whether this is negative or positive, after this operation they will become positive, so definitely this side will be larger than this side. Okay, so that's why we write this is less than or equal to this. Again, you understand e power minus j omega n, so the absolute value of the magnitude of this one will be always equal to 1. So that means the existence only depends on the x of n. If the x of n is absolutely summable, then we say Fourier transform exists. If it's not absolutely summable, you understand that summable means that it gives you some finite value. If it results into some infinite value, in that case we say this is not absolutely summable. So if some signal sequence is not absolutely summable, but if it is square summable, then we say yes, right? So the condition is if the signal is absolutely summable, the Fourier transform exists. For the discrete time signal, again, if the discrete time signal is not absolutely summable but square summable, in that case also we say the Fourier transform exists. If the above two conditions do not hold, then f of t for that signal might or might not exist. Also, if of t might or might not converge absolutely for continuous time signals, right? Specifically, if the continuous time signal has discontinuities, then the continuous time IF inverse Fourier transform converges to the midpoints of the discontinuities, right? So you understand what is discontinuity, and we have discussed about these things in a lot of detail in signal system. And but in case of discrete time, the inverse Fourier transform will always be converges absolutely to each point, because continuity is not an issue in discrete time signals. Continuity is issue in continuous time signals, not in discrete times. So simply it doesn't occur in the issue of convergence doesn't occur in discrete time case. So these are some of the problems, and I want you to go through them and do it right. So these are some of the discrete time signals, and you have to find their Fourier transform. Again, it's another problem that you have the frequency response or the Fourier transform, right? And this is defined as this one, and you have to find the impulse response. So this is the expression for the ideal filter. You understand that in case of ideal filter, we have the response like, so this is your discrete time ideal filter, right? So it has pass band from minus omega c up to omega c, and you understand it will be periodic, it will repeat, right? This is somewhere 2 pi. Again, here we have, for example, minus 2 pi, so it has replicas or copies of this all around there periodic. Okay, so this is the graphical representation for this low pass filter, right? And uh, you are asked to find the impulse response of this ideal low pass filter, and you understand how can you do it. So just using the, you can use the inverse Fourier transform to find the impulse response of this filter. So the next topic is the properties of the Fourier transform, discrete time Fourier transform. So we'll quickly go through them because you have done these in detail in the course of signals and system. Here we are just having the summary or overview of these. Okay, so if you have x1 has the Fourier transform x1 ej omega, and x2 has Fourier transform this, then if we sum and scale these two, right? So you understand linearity is basically, linearity is the if we say a system or transform is linear if it holds the two conditions, and the condition one is that it holds the property of superposition, and the second one is scaling. Okay, so if this produces this one, so if I scale this one by a factor of a1, and if I scale this one by a factor of 2, and then I take the superposition, then the right, at superposition of these, and if I take the Fourier transform of this superposition, it should result into a time x1 ej omega plus a2 time x2 ej omega, right? So if this is the case, then we say this transform holds the property of linearity. Okay, so we are not going to derive this one, but straight away we just mention that it is the Fourier transform holds the property of linearity. Okay, and this is how linearity is tested. Okay, again the next one is we are going to consider is the time shifting. So time shifting means if x of n produces x of j omega n, and then I shift the x of n by some amount, maybe by some amount, and not can be positive or negative, you understand, depending upon the whether and not is positive or negative. The shifted version can be the uh, uh, delayed one, or it can be advanced one, right? So if n naught is positive, then we are delaying it, and if n naught is negative, then we are advancing it, right? So delay shift by amount and not result into the Fourier transform, right? The same as we have for the original one, and we just multiply it by e power j omega and naught, right? So this is how time shifting in time domain results in frequency domain. So if you shift it by amount of n naught in the frequency domain, it will be simply multiplied by e power minus j omega n naught, right? So that we can say that time shift results in phase change only, no effect on magnitude. Similarly, frequency shifting, so if you have x of n has the Fourier transform of this one, so if I shift in frequency by amount of omega naught, then in time domain it will be similar to what we have here. It will be just multiplying the time domain signal by a factor of ej omega naught n, right? So the next property is the conjugation. So if x of n has Fourier transform of this, then if I take the conjugate, you understand conjugate is that we have a complex number, and if you change the sign of the imaginary part, then the resulting will be called as conjugate, right? So if I have a signal x of n, it has Fourier transform of this one, and if I take the conjugate of the input signal, the resulting Fourier transform will be conjugate, and the frequency will be replaced by a negative sign. Okay, so if x of n is real valued, then its Fourier transform is conjugate symmetric, that is magnitude spectrum is even, and the phase spectrum will be odd function of omega. I think you are familiar with the even and odd things. Okay, so the next property is the time reversal or folding, right? So if x of n has Fourier transform x of e power j omega, then if I flip the x of n, okay, then the Fourier transform will have the flipped version, right? So if we combine the two properties we have studied previously, then based on that, x of if we take the conjugate of x and we also flip it, it will be equal to x uh, conjugate, right? The Fourier transform conjugate, and the because of the folding, this effect will be cancelled, right? Because previously, if you recall, we have the folding of frequency also. Then the next property is convolution. So you understand if x1 of n produces x1 of ej omega and x2 of n produces x2 of ej omega, so if we take the convolution in time domain, so it's in frequency domain, it will be simply the multiplication. So that means to avoid convolution, what we can do is we just take the Fourier transform of the both signals, then multiply them, because in Fourier transform they are multiplied, right? Time domain convolution, multiplication in frequency domain. So you understand multiplication is much easier process than the convolution. So we can avoid the convolution by taking the Fourier transform of the both signal, taking the product of those, and then if we take the inverse Fourier transform, we'll get this thing done. So modulation in time domain. So you understand Fourier transform and the time domain and the frequency domain, they are reciprocal in the sense that in time domain, if two signals are multiplied, in frequency domain they will be convolved. Similarly, if the two signals are convolved in time domain, they will be multiplied in the frequency domain. So again, you can do the same trick here. If you are in frequency domain, you have to find the convolution, right? So instead of finding the convolution, you come back, you using the inverse Fourier transform, come to the time domain, take the product of the two, and then take the Fourier transform. So you can easily avoid the convolution. Okay. Similarly, convolution in time domain is basically multiplication in frequency domain. Frequency differentiation. So if you have x of n, it is Fourier transform x of e j omega. Then if I take the differentiation in frequency domain, it's equal to multiplying the time domain signal by n. Okay, and the last property we are going to consider is the Parseval's theorem, and it states that if the x of n has Fourier transform of x of e j omega, so that means if I want to find the energy, so in both domain energy is same. So that means I can find the energy in time domain using the equation, this one. I think you are very well familiar with these equations. So to find the energy in time domain, the absolute square and summing it over from n equals to minus infinity up to infinity. So again, if I have the frequency domain signal, so in frequency domain the energy can be found by squaring the absolute of the signal and integrating it from minus pi up to pi and scaling it by a factor of 1 by 2 pi. So in both domains the energy is conserved, whether you have time domain or you have frequency domain. In both cases you have the same energy, right? So we can also call that the Parseval theorem is basically energy conservation theorem that states that the Fourier transform preserves the energy of the signal when it transforms the signal into the frequency domain, right? So these are the two expressions. This is for the time domain and this is for the frequency domain, and you can easily see that they both will have, you get the same answer. So again, this is the example that we have in time domain. The output equals to the input convolved with h of n. So if I take the frequency domain of the above signal, the above equation, so y of n has Fourier transform y of e j omega, and x of n has x of e j omega, and this convolution symbol will be basically replaced by multiplication. So multiply by h of n has Fourier transform of this. So simply we can do it, right? Now, for example, we need to find the impulse response, and we are given the input and the output. So that's very tedious work here to find the the impulse response, right? So easy one will be that we have the input signal, we have the output signal, so we take the Fourier transform of those, okay, and we can easily find the frequency response from this in the right. So once we know the frequency response, we can take the inverse Fourier transform and we can very quickly find the impulse response. Okay, so the next topic is about the linear constant coefficient difference equations. So this is the generalized expression for the linear constant coefficient difference equation. So we can find the frequency response, right? So for example, you are given linear constant coefficient difference equation, and you have to find the impulse response. So that's very difficult to find the impulse response from here. So what we can do is we can take the Fourier transform of both sides. So once we find the Fourier transform, so y of n has Fourier transform y of ej omega plus, because that's a linear transformation, so if something is scaled by ak, so again it is ak. Now y of n minus k, so if we shift, we have done the shifting property, right? So that means we can, if we shift the time domain signal, right, in frequency domain, it is equal to multiplication by e power j omega, right? Similarly for this one, so you can take y of ej omega common, and you can express it y on one side, x on other side. So h of j omega basically equals to y of j omega divided by x of j omega, which can be done like this. So using this, we can easily find the frequency response, right? Frequency response, and from frequency response, by taking the inverse Fourier transform, we can easily find the impulse response. Note that the frequency response of LTI system is always rational in. So the last topic is the interconnection of the system. So interconnection can be cascade, or cascade, also called series connection. Connection of the system. So you understand, in case of series connection, you have one system followed by the next one. So again, if we see in time domain, the output will be equal to x of n convolved with h1 of n, right? And the resulting thing, whatever you get, will be convolved with this one. So mathematically we can write that y of n equals to x of n convolved with h1 of n convolved with h2 of n. So the impulse response of this overall system can be h1 of n convolved with h2 of n, right? So if we look at these things in frequency domain, so in frequency domain, simply h of n will be equal to h1 of, h of ej omega will be equal to h1 of ej omega times h2 of ej omega. So instead of convolution, we have simple multiplication, right? Similarly, for the parallel connection, we have x of n convolved with h1 of n, and similarly for the feedback connection. So we have, for example, this is the equation for the feedback connection, and here this is the representation for the feedback one. So here again you see that these are convolving, right? So that's very simple, that we can express it in frequency domain, and the overall response of this system, overall frequency response of this system, is h1 of ej omega divided by 1 plus h1 ej omega h2 ej omega, right? So that's very simple to do it, and once you find this one, you take the Fourier inverse, and you get the output of the system. So I think that's all for today. Okay, so just a small part is left, which we'll cover in the next lecture, and then we are going to start the next chapter.